present video, we will be considering the application of the very famous Schrodinger equation to a particle in a one-dimensional box. Let me explain to you what is the meaning of a particle confined to a one-dimensional box. Imagine there is a box. Imagine that we have put two walls, one at x equal to 0 and x equal to a, which means that the particle is free to move in the x direction from 0 to a, but when it comes to x equal to 0 or x equal to a, it will meet the walls, and what is outside, less than 0 or greater than a, is outside the box. So essentially we are imagining a particle, which may be a molecule or an atom or an ion or anything else, to keep shuttling between two fixed walls. And we start with the simplest case of one-dimensional movement, where there will be only one variable, which is x. We are further assuming, and this is very interesting, that since the particle has complete freedom to move within the box, its kinetic energy is maximum or infinite, and therefore its potential energy is 0 inside the box. Also, its potential energy abruptly becomes infinity at the walls and also is infinite outside the box. So therefore the potential energy of the particle is 0 within the box, infinite at the walls and infinite outside. The idea is that a particle in motion has 0 potential energy in this case, and we are assuming that the particle cannot move at the walls and also cannot move outside, and that is why we are assuming that the potential energy is 0 inside the box but infinite both at the walls and outside. Now with this kind of a preliminary understanding or preliminary assumption, let us straight away write the Schrodinger equation. As you very well know, the Schrodinger equation in one dimension, when potential energy is 0, can be given by d square psi by dx square 8 pi square m by h square E into psi. If of course potential energy was there, we would have written it as E minus V. But since the potential energy is 0 everywhere within the box, I am writing it as E into psi equal to 0. Please remember that this is a second order differential equation in psi. To solve this equation, we make a small mathematical adjustment and say this entire term is equal to k square. So that the equation now comes to the standard form d square psi by dx square plus k square psi is equal to 0. And the solution is also easily available from mathematics. The solution can be written in this form, where psi is equal to a sin kx plus b cos kx. At this stage, let me tell you that what I have written is the equation for a particle which is free to move in one dimension, and this is the solution for the movement of the particle in one dimension. I am yet to put the boundary conditions or the restrictions. Please observe now very carefully that the particle has to be found within the box. Since the particle has to be found within the box, psi cannot be 0 inside. The wave function cannot be 0 inside the box. Also, the particle cannot be found outside the box. Therefore, psi has to be 0 outside the box. So here we have a situation where psi is 0 outside, psi is non-zero inside, and therefore psi has to change from a non-zero value to a 0 value, and hence for psi to be continuous, from non-zero it has to become 0, and therefore psi should be 0 at the walls as well, which means that psi will be equal to 0 when x is equal to 0, psi will be equal to 0 when x equal to a. This is a very important point that we need to understand, that the probability of finding a particle anywhere can be given by square of psi. Modulus of psi square gives the probability. Since the particle has to be somewhere within the box, it is quite obvious that psi is 0, non-zero within the box, Since it cannot be found outside the box, psi has to be 0 outside the box, and because psi is a continuous function, when psi is non-zero here, 0 here, it has to be 0 at the walls. So taking the solution, which is psi equal to a sin kx plus b cos kx, when you apply the boundary conditions, suppose you put x equal to 0, then psi has to be 0. So therefore, a sin 0 plus b cos 0 is equal to 0. Sin 0 is 0, cos 0 is 1. So therefore, 0 becomes equal to b, or b becomes equal to 0. When you put it back in this equation, psi becomes a sin kx. So instead of two constants and two functions, now we have only the sine function left. To evaluate the nature of the sine function, let us put x is equal to a, the other boundary condition. When x equal to a, the wave function has to be 0. Therefore, a sin ka is equal to 0. This leaves us with two possibilities. One possibility is that a can be 0. The other possibility is sin ka can be 0. Can a be 0? If a is equal to 0, if I put a equal to 0 here, then psi will become 0 for all values of x, which means that psi will be 0 everywhere within the box, and therefore I can't find the particle within the box, which is absurd. So, for the solution to be acceptable, a cannot be 0. So what should be 0 then? Sin ka should be 0. Then what should be ka? We very well know that sin 0 is 0, sin pi is 0, sin 2 pi is 0, or in general sin n pi is 0. Therefore we can say ka is equal to n pi, or k is equal to n pi by a. Hence, by applying the boundary conditions, we are now able to evaluate the form of k as n pi by a. Hence, we realize that k square is equal to n square pi square by a square, and by assumption k square was 8 pi square me by h square. So simplifying, we get the value of E, which is the total energy, as n square h square by 8ma square. And since psi is equal to a sin kx and k is equal to n pi by a, we substitute back in psi and get the psi as a sin n pi x by a. Please remember that both E and psi depend on the value of n, where n can take the values 1, 2, 3, etc. You will of course curiously say that n can also take the value 0. If you put n equal to 0, then this sine function will become 0, which means psi will become 0. But psi cannot be 0 inside the box. So therefore, n cannot be 0, but it can take the values 1, 2, 3, 4, etc. And hence we can use the subscript en and psi n. I'll be explaining the meaning of psi n and en in detail in the next 5 to 10 minutes. But very quickly let us understand that we have solved the Schrodinger equation. When you solve the Schrodinger equation, the solution of the Schrodinger equation is the wave function psi. The solution of the wave function, the solution of the Schrodinger equation, which is psi, is itself an equation. You can clearly see by the nature of psi that we have obtained. For example, when you put n equal to 1, the first wave function obtained can be written as a sin pi x by a. This is one solution, one wave function. So we are now going to put different values of x, like you do in plotting a graph in your high school or PU mathematics. You start putting different values of x between 0 to a. For every value of x, you will find the value of psi. And when you collect all the values of psi, you will get a sine wave. You will get a sine wave, okay? And that will be psi 1. Suppose you want to evaluate what is psi 2. What is psi 2? It is a sin 2 pi x by a. Again, sine wave is obtained, but of different wavelength. So you will be putting different values of x. You will be getting another wave function. So in this way, by putting different values of n as 1, 2, 3, 4, 5, 6, etc., you will be getting different pictures. In this case, the pictures are all one-dimensional pictures. For n equal to 1, you will get one wave function, which is one picture. For n equal to 2, you will get another one-dimensional picture, third picture, fourth picture, so on and so forth. For each wave function, there will be a corresponding value of energy as well. For psi 1, if psi is equal to n is equal to 1, then the wave function is a sine pi x by a, and when you picturize it, it will be one wave. But when you put the value of n as 1 here, then the energy value will be written as E1. So E1 will be equal to h square by 8m a square. So every wave function corresponding to a particular value of n has a particular value of energy, which means that the values of the total energy cannot take any and every indiscriminate value. It cannot vary continuously from 0 to infinity, but it can take only certain specific values. Now that is because only certain functions, certain wave functions are acceptable, and therefore the energies exist only corresponding to those wave functions. And this restriction is brought about using the number n as 1, 2, 3, 4, 5. So therefore, both the wave function as well as the value of the total energy become restricted or quantized. Therefore, the wave function as well as the energy values cannot vary continuously, but can take only definite and discrete values. This is happening because we are applying boundary conditions here. We are restricting the particle to move between two walls, which is a confined space. The moment you remove the boundary, which means that the particle is free to move in a box of infinite dimension, then naturally what will happen? If you remove the restriction, then the particle can assume any value of psi and any value of E. In the next segment, we are going to understand the solution of the wave functions and also the values of the energy in greater detail and picturize by drawing waves for psi 1, psi 2, psi 3 and so forth.